Welcome to another session of our lecture in stochastic processes. That one will be a short one, and we will be dealing with some measurability aspects. As you know, random variables are measurable if some pre-image of some sigma algebra is a subset of some other sigma algebra. That's clear. But for stochastic processes, we need a bit more because we have the time axis and the state space axis. So there is more to say about stochastic processes, and we will come to that now. So the keyword today is progressive measurability, which is something a bit more than usual measurability. That's a short video, and we will discuss basically these three things here. First, what is progressively measurable? Then we have a statement, if we have a stochastic process which is right continuous, then it is progressively measurable. And if I have a process which is progressively measurable, then this thing here, xt, which we had already, so x evaluated at the stopping time t here, that's a random variable, which means it's measurable. That was not clear up to now, but with this proposition here, it becomes clear. So, what is progressively measurable? So, xs, for example, as it's written here, that's a random variable. And that means that omega maps to xs of omega, that's measurable. But progressively measurable means that the tuple s comma omega maps to xs of omega, that's measurable with respect to a product sigma algebra on the times and the space. And that's just the product sigma algebra, like this here. So that's a bit more, because I have measurability in the time and also the state space component. So let's see how this is. The first lemma. If I have a right continuous path, then I have a progressively measurable stochastic process. In order to do so, let's consider exactly the map that we had on the first slide. Let me briefly recall that. Why I call this here I intersected with 0t times omega to e, and s comma omega maps to xs of omega. So this is exactly this thing here. I have, well, two cases, and one is pretty basic. I is either countable or has right continuous paths. So if I is countable, then y to the power of -1 of any set b, so b is a measurable subset of e, because it maps to e here. Well, how can y be in b? It has to be such that for some s in e, s smaller or equal to t, xs to the -1 has to be, xs has to be in b, and well, s times this here. And this here is measurable. And the point is here that this union is a countable union because I is countable. And here I have the single things which are measurable, and they are measurable, and that's not a big deal. More interesting is the case where x has right continuous paths. And the point here is that we can define xs_n, we can approximate xs by going from s in a discrete setting from the right. So if I have my time here, I have my s here, and well, in the nth step, approximate this by 2 to the minus n and the bracket process 2 to the n s. So this here is, sorry, I have to be precise here. So not rounding, but taking the ceil function, which is the, so this here is the number which is bigger or equal than 2 to the power n times s. So the smallest number which is bigger or equal to this thing here, which means that the whole thing here is bigger or equal than s. So approach s here from the right. So this process is exactly this. I approach every s from the right, 2 to the power minus n, 2 to the power n s. Okay, make noch min t here because I'm restricting myself to 0t here. I'm doing this for n from 1, 2, and so on. And yn is the corresponding thing. I just write n corresponding yn. Then yn goes almost surely to y as n goes to infinity, because x is right continuous. So this thing here for every t goes to xs. So y, which I want to have measurable, is a limit of yns, and the yns, they are nicer because they only jump at discrete time points. And now I can write yn to the power minus n of b equals, well, that's similar as above. I have a union, and the union goes over all k such that k plus 1 to the power 2 minus n is more equal to t. That's valid for the time points k to the 2 power minus n until k plus 1 2 to the power minus n. And yn is in b, that means x at this time point is in b, so xn is in b, which means x is something, and x has to be in b at the time point k plus 1 2 to the power minus n, because this is the value xs to the n has at all time points between these two things here, between two jumps of xs to the power of n. And now I've done everything, because so this here is measurable because it's well, the whole thing is measurable because it's a finite union of measurable sets, so that's measurable. This is also measurable because xs is measurable, countable or finite union, and the limit of this. So y is measurable as a limit of measurable functions. And that's it. So last, progressively measurable means that x at evaluated at a stopping time is measurable, which is of course a nice thing to have because we want to write down xt and want to do things with it, what we basically want to do with random variables. Well, how does this work? So I have to show the following. I have to show that xt in B on the set t or smaller equal to t is in ft. Well, yeah, I have to show that it's measurable, and it's measurable with respect to this sigma algebra here. And we had that last time. Elements of this sigma algebra ft have the property that, well, on the set t smaller or equal to t is in ft. Okay, so we have to show this here for be measurable. Yes. And look here, we are evaluating this here on the set t lesser or equal to t. Yeah, and basically that's the same as doing the infim with t here, because on the set t bigger than t, I'm not counting this anyway. And that means I can use here that t is bounded, so without loss of generality, we have t lesser or equal to t, because I can write that down like this here, and I'm not changing the event. So big T is bounded by small t, and I have to then say, well, yeah, I can use this here. And in the case that big T is smaller or equal than small t, I can, write xt equals yt composed with psi of omega equals t of omega comma omega. And yt is the yt that we had here, so call this here yt. So first use this thing here, and then use yt. So what does that give me? First, when I evaluate psi, which is t of omega, comma omega, I have here t of omega, comma omega. That's x t of omega, comma omega. So it's of omega. That's exactly what I want to have to be measurable, so that I can just write it like this here. And I have to show that xt is measurable. And I'm doing this by saying, well, these two things here are measurable. So how are they measurable? Psi measurable with respect to, well, t is a stopping time less than or equal to t, so that's measurable with respect to t. On the one hand, on the other hand, I have it like this here. I intersected with 0t times ft. That's where it maps to. So it maps to the omega here is measurable with respect to ft. And that's by progressively measurability. So that's exactly as written here. That's measurable to this here, and the fs is of course a subset of ft. And I can use this because yt is measurable with respect to something else. That's measurable with respect to I intersected with Borel sigma algebra 0t times ft b of e by progressive measurability. So that's exactly as written here. And I have a composition of two things. So the first one has this measurability, the other one this here. And the result, the composition, is then measurable with respect to ft B of E. And that's what I wanted to have. So I wanted to have that this here is in Ft for all B in BE. And that means exactly that's measurable with respect to this here. Okay, that's it already for today. And I hope to see you next time. Bye.